Standard electrode potentials. Okay, standard electrode potentials. Okay, as the Siyavula grade 12 textbook does tell us, is a measurement, all right, of the potentials that happen at equilibrium, or equilibrium potentials. Okay, there are three conditions for the what's the word I'm looking for for this equilibrium to be tested at, or for this equilibrium to be achieved. So there's conditions for this type of equilibrium. All right, pressure, temperature, and concentration. The pressure does need to be at 101.3 kilopascals. The temperature must be at 298 Kelvin, which is basically 25 degrees Celsius, and the concentration must be at 1 mole per decimeter cubed. All right, if you're going to test the standard electrode potentials at any time. Okay. The definition for a standard hydrogen electrode, okay, is that the standard hydrogen electrode is a redox electrode which forms at the basis of the scale of oxidation reduction potentials. So in the textbook here, they've given you half reactions, or they've given us the table of standard electron reduction potentials, or standard electrode potentials. Okay, in brackets they put their reduction. Okay, so what they've done here is we must understand that the standard electrode potentials, or standard table of reduction potentials, we must understand that on both tables 4a and 4b, okay, this table that they have inserted in the textbook here is table 4b, with the lithium half reaction on top at minus 3,04 volts. Okay, so what's happened there is, this is table 4b, but in both tables the reactions are written in reduction half reaction format. So they are all written like this. Even if the bottom is on top, they're all written like this. In other words, it's not written the other way around. They're all written like this. So the question probably on everybody's mind probably right now is that obviously the one table starts from a positive value and the one table starts on a negative value. But what does a negative and what does a positive value in this little section or column of the table mean? Okay, so what that means is that sometimes we have something called the electrode potential, which is obviously represented by this symbol. Okay, the electrode potential, which is also basically saying of a half cell, right, which is measured in volts, can have two values. Okay, if we take this one example over here, all right, I'm going to use silver again. So if I have Ag plus, that plus 1 electron, that gives me Ag, just like that. I haven't written the states in, but the electrode potential that this cell has is equal to 0.80 volts. Okay, decently high. Okay, this is classified as a large positive electrode potential. Okay, and we obviously want to know what does that mean, and I'm going to share it with you in just a moment. So a large positive electrode potential does indicate, okay, it indicates that a substance will probably be oxidized. Sorry guys, I know I mentioned that indicates the substance will probably be oxidized. Sorry, that's incorrect of me. Let me just correct myself. A large positive electrode potential, that indicates that a substance will probably be reduced, meaning that it has a stronger, or is a stronger oxidizing agent. All right. So I do apologize for that misquote. That's if we see a fairly large positive value. So even if you look at the table 4a, we just go down to the bottom. I see as we go further down on table 4b, in table 4b, as we go down the table, we do see increasing oxidizing ability as we go down the table, but as we go up the table, we see increasing reducing ability. So definitely when you see this table of this value, positive 2.87, you know that substance is definitely going to be reduced. Okay, having a look at another substance here. Here's silver that we saw in that example. Another example, gold, right, and that's cobalt. Another positive value. We also see, yes, the copper 2 plus, right, which we know in the zinc copper cell, galvanic cell. Copper is the substance that is reduced. Sorry, this one over here, not that one, this one over here. We can see that obviously in this table. The next part is what happens if we see a negative substance. So now we have again in the table, and what I'm going to use is use lithium. All right. So the reaction is obviously not written the same way because lithium is a substance that is obviously has become oxidized. But this one, lithium, has an electrode potential of minus 3.04 volts. Here we go. So this is a large negative electrode potential. It's fairly large because it's 3 point something. Here we go. Okay, so now if a fairly large positive electrode means that the substance will most likely be reduced, then the opposite is true for this oxidation half reaction here. For a large negative electrode potential obviously indicates that a substance will most likely be oxidized. Okay, because it is a stronger reducing agent. Right, stronger reducing agent, as per the example over here that you see there. Okay. So if we had to write that also in cell notation, because it's a stronger reducing agent, it'll be lithium becomes Li plus salt bridge and whatever else is there. Okay, so that is just explaining, of course, the standard electrode potentials and what those values obviously mean. All right, and the formula for calculating the electrode potential of a specific cell. I know I shared this last week, but I'll share it again. That the cell potential is equal to the cell potential which is at the cathode, which is where the more positive values are, minus the cell potential or electrode potential at the anode. Okay, that's the standard formula. Please don't forget it, because that's what you're going to use to calculate. One is the electrode potential of the cell, which is known as obviously cell potential in this case. Okay, so it's also called cell potential, by the way. It's also called the EMF, or potential difference, and what that does is it does provide the driving force that causes electrons to move. Okay, and probably if I've not mentioned this, then please take this step down, or this sentence down. Electrons, they do move from anode to cathode. Okay, they do move from anode to cathode. Taking just a little bit of example, we're having a look at the standard electrode potentials. Again, we're looking at copper and silver in this example. Okay, and again, they have just said that the following reactions take place in an electrochemical cell. Okay, and they have written the reaction, okay, or the reactions straight from the table of standard reduction potentials, okay, and all they have done is they've just written the reactions in the reduction format, okay. So they, at the moment, looking at it, they both look like reduction reactions, but we know it's impossible. One substance is being reduced and one substance is being oxidized. Okay, determine which reaction is the oxidation half reaction and which is the reduction half reaction. Okay, now from the table of standard electrode potentials, if we go and find out just looking at the reactions in this format, all right, just go find out what is the electrode potential. Okay, we can see that the copper 2 plus reaction we find has a electrode potential of positive 0.34, and the silver has a positive 0.80. Now, interesting thing to note here. One, they are both positive, and we know that what we've just learned, that a more positive electrode potential indicates the substance will most likely be reduced. Okay, so looking at the solution, step 2, both values are positive, but silver does have a larger positive electrode potential than copper. So now that answers the question of, JP, what do I do in that case if both my electrode potentials end up being positive values? Well, what you'd have to do is look for the one that's obviously more positive, more strongly positive, has a larger positive value, and we can see obviously in that case it was silver. Okay, and when I teach you how to read the table, I'll show you how I would have known that without even comparing values. Okay, so we found that copper obviously is more, silver is more easily reduced than copper, and copper is more easily oxidized than silver. Okay, this is obviously different comparing it to the zinc copper cell, because zinc has a negative value. Zinc has a negative electrode potential value of negative 0.76. So and copper obviously has positive 0.34. So in the zinc copper cell, we know that obviously zinc would have been oxidized while copper would have been reduced. Alright, cool. Moving on. Step 3, write the reduction and oxidation half reactions. Okay, now we know that which substance is being reduced and which is being oxidized. We can go ahead and write them correctly. So know the reduction half reaction we keep the same as we were given it. So Ag plus 1 electron, or e to the minus, gives us Ag solid phase. And the oxidation half reaction, we write it, looking at this part here, we write it from right to left. So Cu copper, Cu in brackets S, gives us Cu2 plus in aqueous plus 2 electrons. Now before we continue maybe to look at another example, I think it would be great for me just to jump in just to show you how the table of standard reduction potentials work. Okay, and I'm going to draw it. First going to write out a half reaction for you, and I'm going to explain which table first. Okay, I'm going to pick table 4A first. Table 4A is the decreasing reduction potential. And I'll tell you, and obviously it says that, but I mean, I'll draw it out still, and I'll say this is table 4A. Cool. Okay. So again, it's a table of half reactions. All right, it's well-known redox pairs. Okay, they have been tabulated for us, and they form the list, obviously, of standard electrode potentials. Okay, and it has been written by convention. All right, the half reactions in the tables, all right, 4A and 4B, are listed in such a way that the forward reaction is a reduction reaction. Okay, it's written in such a way that it is a reduction reaction, and the general formula for reduction reaction is OA, meaning the oxidizing agent, N plus meaning the charge. Right, if it's 1, then it's just plus. If it's 2, then it'll be 2 plus. Okay, oxidizing agent plus the number of electrons, N stands for number, and the product we get from that is the reducing agent. Okay, but it's obviously the reaction in the table is written like this, with the backwards and forward arrow, and we have the reducing agent. Okay, so it's written by convention in both tables, all right, that such that the forward reaction is written as a reduction reaction. That's why it's called the table of standard reduction potentials, because all the reactions have been written as reduction reactions. Okay, but we know obviously that not all reactions take place as reduction reactions, because some substances are oxidized and some are obviously reduced. But table 4A is the decreasing reduction potential, or decreasing reduction potential table, meaning that the strongest reducing agent, okay, is at the bottom, all right, and the strongest oxidizing agent is at the top. Okay, that's how it's written. That the strongest reducing agent is at the top, and the strongest oxidizing agent is obviously at the bottom. Okay. Therefore, the most negative, because the strongest reducing agent is at the bottom. Okay, that's what I think. That's what I said. Yes, the strongest. You know me, I mix up my words sometimes on a Monday. That the strongest reducing agent is at the bottom. So that means that the half cell with the most negative reduction potential is at the bottom. Okay? And the strongest oxidizing agent is at the top. Therefore, the half cell with the most positive reduction potential is at the top. So if we take a look at the reactions for that, written like this, so we have F2 plus 2 of the electrons. We have the forward backward lines, reaction arrows, and we get 2F to the minus, and that has a cell potential, of electrode potential rather, of positive 2,87, and all the way at the bottom we have the lithium reaction, Li plus 1 electron, forward backwards reaction gives us Li with a electrode potential of minus 3,0, depending on your table of standard reduction potential. Sometimes we'll say 0.04 or say 0.05. Say 0.04. So I'm basing it off this table over here that we saw. Sorry, I scroll a little down. There we go. Basing off that little value there. All right. So how this works is that for the decrease in reduction potential for table 4A, you basically got two arrows coming down. Okay, you got one arrow that is going up, and you got one arrow that is going down on either side of the table. Okay, arrow that is going up like that, and one that is going down like that. So what's happening with the arrow that is going up? Okay, that means the reduction potential is obviously increasing, meaning the strength of the oxidizing agent is increasing. So this is a strength of oxidizing agent, OA. And at the bottom here going down, we just keep it right in like this. Coming down, I've got the strength increasing of the reducing agent. Okay, in other words, the oxidation potential. So let's write that there, oxidation potential. And this is reduction potential. Hope you all can see that, but it's reduction potential. Okay, so that's how table 4a works. Okay, that we have the strongest reducing agent on top and the strongest oxidizing agent at the bottom. So table 4a helps if you just want to look at which substance is obviously being reduced. So the reduction half reaction is easier to find because you just look for it at the top. Okay, and that's how you understand the table. So another way to understand it, again using arrows, is that use another color. So going this way, you have your reduction half reaction. Make my pen a little smaller. You have reduction, half reaction, so I'm going to use HR. Okay, and then how you read the bottom part is that way, going from right to left, is your oxidation half reaction. Okay, and that's obviously, the arrows obviously as you go up the table. So as you go up the table, we got oxidation half reaction going all the way up through the negatives, and then once you get your positive values, so obviously reduction will go on top. That's how you look at it, and that's how you read table 4a. Table 4b is exactly the opposite. Okay, so it's exactly the opposite. Okay, so we always reading it like this, in clockwise mode. Always table 4a is read in a clockwise direction, because reduction, as you come down, oxidation. Okay, obviously the other way is anti-clockwise. Okay, because we've got oxidizing agent on top. Okay, and then going all the way down, we've got the reducing agent, etc., etc. Don't have to explain that again. Obviously, everybody understands what I'm trying to say. That's how you read table 4a. Table 4b is a little different. So table 4b, all right. So what happens with this one? The reactions are written in now, starting with the negative on top, and the positive is at the bottom. So in other words, the strongest reducing agent. Okay. Oh, I need to change this name as well. One more thing I need to change. Instead of this being a decreasing, this is table 4b is actually not the decreasing reduction potential, but it is the increasing reduction potential of table 4b. So the difference is the difference is that the strongest reducing agent now is at the top, and the strongest oxidizing agent is now at the bottom, which means it's at the opposite to table 4a. So if we just write out again the reactions, so now the lithium reaction is going to be written like this. On top, it gives us Li with the cell potential 0.4, and now at the bottom we got the F2 plus 2E, which gives us 2F minus plus 2.87. Alright, so that's the only different. The arrows also switch. So the strongest oxidizing agent reduction potential this arrow is going down, and the strength of the reducing agent is now going up. Alright, so how the table is read for this one in an anti-clockwise direction, it's written going like this. If you read the table now like this, you have the oxidation half reaction. Okay, so oxidation HR half reaction. Okay, then as you go down the table, eventually when you get to the more positive side, you now read the reduction half reaction. Alright, and that's how reading those two tables essentially work. Alright. Maybe just to have a look at oxidation and reduction potential. What does that mean? So reduction potential is potential to be reduced, alright, itself, but reducing ability is the ability for to reduce another substance. Okay, when we say reduction potential, we're talking about the substance or the potential to be reduced itself, not to for the substance ability to reduce another substance. So usually both tables for A and B, they are provided in your exams. Usually they are. Alright, and in some textbooks as well that have them, some textbooks that come with past papers, won't mention any names though, they should include them in, especially in their those study guide like textbooks. Okay, either one can be used. However, you need to decide beforehand which table you prefer. So you might prefer the table 4B with the strongest reducing agent at the bottom and the strongest oxidizing agent on top, or you might prefer the table with the strongest reducing agent on top and the strongest oxidizing agent at the bottom. Okay, however, if you want to use both, you definitely can. I know when I was at school in the exam, I used both. So if you want to have a look at calculating the cell potential of a galvanic cell, we remember that the formula is that the cell potential is equal to calculating the electrode potential at the cathode minus the electrode potential at the anode. Now there's more than one way also to write the same thing. You can write that the cell potential is equal to the potential of the reduction minus the potential of the oxidation reaction, okay, or of the oxidizing agent minus the reducing reagent. Now for zinc potential, for a galvanic cell, and especially with example for a zinc copper galvanic cell, how would this look if we had to include numbers or values? Okay, so we'd write it out that the cell potential is equal to the value for the electrode potential that happens at the cathode. We know that that substance is copper, is positive 0.34. Okay, we're going to subtract that from the anode, which is zinc, and that has a value of negative 0.76. So positive 0.34 minus 0.76, which we know ends up becoming positive 3.4, positive 0.34, sorry, and we're going to add that to positive 0.76, which gives us a cell potential of 1.1 volts. Okay, not just 1.1 volts, but 1.1 volts at 25 degrees Celsius and or 298 Kelvin, and at the concentration of 1 mole per decimeter cubed. Remember that if we're going to calculate this value, it must be conducted with under those three conditions. Now, we can obviously see that the value for the cell potential is positive. What does that mean? A positive value, okay, so if this is positive, okay, what this means is that the reaction will take place spontaneously. Okay, so a spontaneous reaction will take place. Okay, positive value also indicates that the forward reaction of the redox process is favored. Alright, that's another one. Okay, so just like with chemical equilibrium, we find out which reaction was favored. Well, the forward reaction is favored here. Alright, and the higher the value, the further the equilibrium lies to the right. Okay, so what we'll do, that's my lesson for today. Okay, that's my lesson for today. In other words, I've got nothing further that I wanted to share with you guys today. We have one more cell to complete, guys. One more cell, and that is the electrolytic cell. Having a look at the redox reactions that take place in the electrolytic cell, and we have quite a truckload of examples that we need to practice. That takes us to the end of chemical change for your matric here. So one more cell and just a little bit of examples on each. So next week we come back and we'll spend some time looking at examples on galvanic cell reactions and that happen there, because there's not just the zinc copper galvanic cell as we saw. We can have other electrodes in there as well for the anodes and for the cathodes. And then we have a look at the reactions happen in electrolytic cells, and then of course we will be done. So that concludes my lesson for today. Thank you so much for joining me, guys, and we're done, and I'll see you all next week.